All right, class, let's try another solution here. And a pretty hard one here, I think, because we've got to go through some geometry. And let me run through the geometry again. But you know what? I would give a hint in this problem that you should probably make a note card and write down the geometric structure. I hope I said that in the video lecture. Write down the answer to this and then have that note card handy when we do the exam, okay? Because on this problem, I would expect you to go back to the video lecture or that note card that you made, and then just write down the formula and kind of plug and chug. I'm going to take a little longer because I'm going to rederive that formula. And we kind of have to anyways because the problem says draw. So let me just start here with a convex mirror. Okay, so if we had something over here, okay, so I'm going to put an object. Nothing real exciting, it's an arrowhead. But the nice thing about an arrowhead is it has a height and it points in a particular direction. And so we can see what happens then on the reflected light to see if it's bigger, if it's smaller, if it's inverted, if it's real, or if it's virtual. So arrowhead works really good for the object. Okay. Let's see, as a convex mirror, so that means it would be curved this way. So the light's going to come in and hit a convex surface. Now it has a focal length. Okay, so focal length is half the radius of curvature. So if I were drawing back, I might say this would be the focal length, or the radius of curvature, and half of the radius of curvature, so we'll call this C for the center. And half of that is then the focal length, okay? And they even tell me the focal length is 60 centimeters, okay? Draw the ray diagram to find the location and the magnification of the image of the object that is located 30 away. Ooh. Now maybe I need to redraw this because I did not draw this to scale well. If this was supposed to be 60, then this was only supposed to be 30. All right, so I'm going to do it again. I'm going to give this one a little less curvature. So the focal length is back here at 60. And then about half of that is going to be my object. Okay, so let's do that. Okay, so now the two beams of light that are worth drawing are the ones that is going parallel. It will bounce off as if, and so I'll do a little dotted line, as if it was coming from the focal point. Okay. So that's what would happen to the light coming from the top of the arrowhead that starts off horizontal, what we call the optical axis, hits here and bounces off. Okay, now another one to draw, and there's 4 easy ones to draw, but we really only need 2 here, is to say what would happen to the light that was kind of already heading towards the focal point. Now, of course, it wouldn't actually go inside the mirror, so I'm going to put a dotted line. Actually, I kind of like that dotted line. I should have done a dotted line with the other one. See, I would have had a better drawing. Well, no big. But this one here would come in and bounce off and go parallel. And then have the appearance of coming from, say, that dotted line. So somebody standing over here would get these 2 rays, and in their binocular vision would say, well, where does that ray, as we trace it back to its origin, and this ray trace back and appear to be together, and it would be right there. And so this is our image. So we called this the image distance, and so for this class we use d sub I for image distance, and then this d sub O is the object distance. So the object, how far it's from the mirror, and then the image, where does it appear? And so this appears to be inside of the mirror. Okay. Now keep in mind that all the way back to here is the focal length. Okay. And of course, keep in mind, then we'll call the height of the object h, but the height of the image h prime. All right. So I guess this is the first part, draw the ray diagram. Okay, so I've done that. But then let's use that and use some geometry. And there's two sets of similar triangles that are nice to work with. Let me draw, say, this one in green. I'm going to take this line where the light was heading down towards the focal point. Now, of course, the light really didn't get to the focal point. It bounced off. But I'm going to draw my line that way. So I'm going to draw a green line all the way to the focal point. I'm going to draw a green line on top of the object and then across the center line here, okay, where the bottoms line up, the optical axis. Now, if you look at another triangle, so here's the height of the image. If you take the height of that image and you just kind of move it to the position of where the mirror is, okay, so that's the height of the image. There would be then this big green triangle, and inside of it would be this small green triangle. And clearly those are similar triangles. So you can write something like this. Height of the image, so height of the image is to the object. Height of the image is to the object. As this leg, which is focal length, is to this whole distance, which is, this whole distance would be focal length plus distance of object. Now, we'll hold off on that one because there's another similar triangle we can do. And I'm going to use this. And I'll draw it in blue, so this blue one here, okay. And then, of course, I drew that one because if you take the height of the original object and you kind of place it in the position of this mirror like that, other than a little bit off because of the curvature, but if you give me a little wiggle room here, and so approximately that's it. So look at this blue triangle, which does cross the actual height of the image there. So I'll make a small blue one inside of it. But these two blue ones, the big blue one here and the little blue one here, are also similar. So we can do the same thing. The height of the image is to the height of the object. So height of the image is to the height of the object. As this distance, now that's a little harder, but let me take it as focal length minus image distance is this distance. So focal length minus image distance is to this whole distance, which is focal length. Yay! Okay, so these are the two equations that will become really powerful if you ever see a problem involving a, what are we doing, a convex mirror. And by the way, our convex mirror, and in the next chapter we're going to have a lens, although we will call it a concave lens, so that's a little confusing, but this same set of equation works for the convex mirror as for the concave lens. So that's coming up next chapter. But this is the one where I'd make a little note card. Make a little note card and say, okay, this is my formula, and so if you come across it, you could have actually have started this problem right here. Although this one did ask you to draw it, so I guess you do have to draw it. But now we can plug in some numbers because this one says find the location and find the magnification. So let me start with the one in green. The magnification, let me just call it MAG, is this ratio. How big is the image compared to the object? I just wondered. Forgive me. I need to go back to the video lecture. I might have put height of image and height of object. I bet I did. It's my other class that uses the H prime in the textbook. Okay, so let me write it that I think is the way it's written for you guys, so I don't confuse you. Okay. Hey, I like that. Hi-ho. Ha-ha. Okay, but no. But it's height of the image compared to the height of the object. So that's what they're looking for. They're looking for the magnification. And it just clearly says it would be the focal length, which is 60, over the focal length plus the distance of object. And so that would be 60 plus, what would they say? I believe it was 30. Yeah, 30. And so that's 60 over 90, and that's 2/3. All right, so the magnification is 2/3. That's saying that, and you can kind of see it in the picture, that the image appears to be smaller by about 2/3 compared to the original object. So, yeah, there's the magnification. And then, of course, the other one says the location, and so that one would be in the blue. So I'll grab my blue pen, but would be looking for that right here. What is that number? Now, notice it's equal to this here, which is the magnification. So I'm just going to take that, a magnification I just did. So there's 2/3, okay? And then set that equal to the 60 minus the distance of the image, and then divide that by the 60. And now I have to go through some algebra. So when I cross multiply, 60 times 2 is 120. This I'll cross multiply and distribute, so that 3 times 60 is 180 minus 3 times distance of the image. I'll move that over to here. That's 3 times distance of image. I'll move the 120 over, so that's 60. And then I'll divide both sides by 3, and I get an image distance then of 20. And we're in centimeters, so 20 centimeters. Yay, hope that helped.